Welcome. Let's look at topic 1.8. And topic 1.8 today involves using the squeeze theorem. So we're going to understand a little bit about how to develop the squeeze theorem and then some of the results of the squeeze theorem. So what is the squeeze theorem? The squeeze theorem really gets down to the fact that you're squeezing a function between two other functions. So you'll notice I have three functions labeled here, g, f, and h. And g and h always are either greater than or less than that middle function f of x. And there comes a point in time where the two functions really come together, but yet f of x is still residing between them. And the limit as we approach c will take on the value of either g of x or h of x for f of x, because it's being forced into the betweenness between g and h. So if I know what g and h's limit is, and it's the same because they're squeezed together, then f must take on that same value. So you'll notice there's an ordering of our functions. It says here that h is less than f, which is less than or equal to g, for all x's in the open interval containing c, and except possibly at c itself. So that is the scenario that we are seeing in our diagram. Then the limit as h goes to c of, as x goes to c of h of x equals some limit which matches the same as the g function. If that is the case, that our two functions have the same limit, then the other third function, the between function, is forced to take on this same limit value L, because it's squeezed together there at that spot, x equals c. All right, there's some special trig limits that go on that are a direct result of this theorem. So one of them says the limit as x goes to 0 of sine x over x, we get the value 1. And these are ones that you really just want to commit to memory. What happens if I take and turn this upside down? I still get the value of 1. So notice that the limit of sine x over x can also be written as the limit as x goes to 0 of x over sine x. What about cosine? The cosine value goes to 0 when I have 1 minus cosine divided by x. And the other one here becomes undefined. Oh, I guess it's twisted around. Cosine x minus 1 over x is 0. The one I was thinking of that I was expecting was what happens if I reciprocate this expression and put x over 1 minus cosine x. Unlike the top where we can flip and reciprocate, this one we cannot. This one does not exist. Okay, so let's use these special trig limits. This one especially is used often in the AP exam, this one somewhat. So the limit as x goes to 0 of tan x over x. Maybe you recall from pre-calculus, tan x can be rewritten. Because if I use substitution, I'm dividing by 0. That's not good. So I'm going to say the limit as x goes to 0 of sine x over x, sine x over cosine x is what tangent is equivalent to, and then I divide by x. But that is equal to what? Well, I could say it's sine x over cosine x times 1 over x, right? That's like x over 1, and then I multiply by the reciprocal, because dividing by a fraction is like multiplying by its reciprocal. Now, there is a multiplication property that allows us to regroup things, so I would very conveniently like to have these two change positions. And my motivation for doing that is that I've got a product going on, a limit of a product. Well, the limit of a product is equal to the product of the limits. The product of the limits. So let's write that out. Now, can I solve for these? This will go to 1 because that is the special trigonometric limit. And then this one, if I plug in 0, what will I have there? I'll have times 1 over cosine of 0. And the cosine of 0 is 1. My answer turns out to be 1 for problem example number 1. Example number 2. Well, when I look at this special trig limit, I have x over x. But that could have said 3x over 3x. It just has to have the same value over the same value, the sign of something over that same argument, that same something. So what I'd really love to see there is a 4, because then this is a match, just like it was a match over there. How can I get a 4 introduced? Well, the only way I can think of is to multiply by 4 over 4. That's like multiplying by 1. All right? Well, then we can do a little bit of convenient maneuvering around, and I can say I've got sine of 4x over, let's multiply those two together and show it. So I got 4x there, times left a 4 there. And the sine, these end up being separate limits. The limit of products is equivalent to the product of the limits, and the first one, this will go to 1. So I'm going to have 1 times the limit of a constant is the constant, so our answer is 4. All right, find the limit as x goes to 0 of 1 minus cosine squared of x over x. Shoot, if it's squared, otherwise it would have been similar to that, but that's not going to work, is it? This is a difference of 2 squares. We could factor. Let's factor that top and see what happens. So, often you resort to just kind of gut feel, and I recognized that I had a difference of squares, and I thought, well, I can factor that, so I'm going to just give that a try and see if that's productive at all. So I'm looking up here at my special rules, and I notice I have a 1 minus cosine x, which I've got, over x, which I have as well. So I'm liking that. I can do some work with that. So this will equal the limit as x goes to 0 of 1 minus cosine x over x times the product of individual limits here of 1 plus cosine x. I could think of that as over 1. So really what I did is I moved this over and kind of created that denominator of 1. 1 times x is still an x denominator, and that works. So now let's evaluate. The limit as x goes to 0 of 1 minus cosine x over x was 0, according to our rules, times, plugging in 0 here, I would have 1 plus cosine of 0. Cosine of 0 is 1, so I'd have 1 plus 1 is 2. But anyhow, it's getting multiplied by 0, so it's going to turn out to be 0, isn't it? That's one approach for that. There's another way, too. You could have started off and said, I recognize that Pythagorean identity from trigonometry, and I could have said 1 minus cosine squared is equal to sine squared, and then worked that as sine x times sine x for a sine squared over x. This limit's going to 1, and the limit of sine is 0, so I would have gotten 0 as well. So both methods end up giving us the same answer, which is a good thing. All right, the next one, example 4. I see sine involved, so I'm kind of hoping I can maybe make use of that special trig limit. But I need an x on the bottom. Can you see a way to get an x? Ah, look here. They both have an x. We could use the idea of a GC, a GCF. All right, let's proceed. I think we're on to something. The limit as x goes to 0 of 3 sine x over x, 5x plus 1. With a little bit of maneuvering, I can bring the 3 out front because it's just a scalar, it's a multiplier. And I can write that as sine x over x times the limit, right? The limit of a quotient is, I'm thinking of it more as a product because of the way I'm grouping it. I'm grouping this together, and then that's going to leave me a 1 over 5x plus 1. X goes to 0. So we know we have 3 times 1 times plug in 0, and I have 1 over 1. Looks like our answer is 3. This was the limit that went to 1. Okay. And that leaves us example number 5, our final example for this section. They're identifying 3 different functions, f, g, and h. And I know I've got a negative x squared and a positive x squared, so that would have to look like that, wouldn't it? And they share the vertex 0, 0 together. And then I end up with this function. And it says, use the squeeze theorem to show that the limit as x goes to 0 of f of x is equal to 0. So the big question is, based on that theorem, is f of x between h and g for some open interval containing c? So here's my c. I want it at 0. And would this function be contained within? So if I plug in 0, I'm going to have cosine of 0 is 1, but times 0, that would be 0 as well. I do believe f of x is squeezed between h and g. So h would be this smaller one. So I know that I have h of x is less than or equal to f of x, which is less than or equal to g of x. And for an open interval near x equals 0. Now, we should be able to do our calculator and see what value this takes on. I have to say that I know the limit as x goes to 0 of h of x, that would obviously be 0, will be less than or equal to the limit as x goes to 0 of f of x, which will be less than or equal to the limit as x goes to 0 of g of x. And because I can calculate out this one as 0, and this side, g of x, evaluated at 0, turns out to be 0, it squeezes the limit. That's right, so by the squeeze theorem. So by the squeeze theorem, the limit as x goes to 0 of f of x must also be equal to 0. And the picture, I'm going to bring out my graph. I did it on Desmos, and that was what it turned out looking like. So we could identify, and you can sketch this out, my h of x was the negative x squared, if I remember right. Yes. So my red function is h of x. My green function is f of x. And my purple function in this case is g of x. So we were able to find out what f of x evaluated at x equals 0 as we head towards that. We were able to get that. Your homework is going to be this Skill Builder worksheet 1.8. Looks like there's just 6 questions. So this one's nice because it's given you a nice orderliness. So I could just think of the limit in front of each of these functions, and we want to check out as it goes to 4, what is happening to f of x. Well, I can plug in 4 to that one. I can plug in 4 to that one. Hopefully they're really close together so that we force the limit as x approaches 4 of f of x to take on the values of h and g. Very good. That is all I have for you.